Hey, what up, y'all? Sorry about the delay of game. Last night I was streaming. Wait, hold on. Have you guys ever heard of the game Dark Souls?
Yeah.
Dark Souls is one of my favorite games, and a lot of people don't know that before Dark Souls, that same company, who's blown up since Dark Souls came out, they're called From Software. They've actually been making games since the 90s. And so there are Dark Souls type games going all the way back to the PS1. Back then they were called Kingsfield. I've been doing like a run of Kingsfield on my Twitch channel. And to run that from my like downstairs game room, I have this USB video capture card hooked up to my PS1. And this morning it was running and I like unplugged it. And I guess my computer really doesn't like having that thing unplugged while it's streaming video, because my computer did a hard like blue screen crash. And then when I restarted it, it had to do a really long recovery process. It's like slow to start up and a little bit weird right now. Um, but I guess we'll see as we move along. I only give this disclaimer in case I have technical difficulties midstream. Nonetheless, please consider the following warm-up question. The ancient Greeks played a game, gambling, like alley gambling at the market, right? With 5 3-sided dice. Each dice has 2 red faces and 1 blue face. So you take the 5 dice, right, that you're rolling in this game, and you roll them. And if you get 3 blue dice, you double your money. Or if you get 4 or 5 blue dice, you triple your money. So analyze this game using binomial expansion. So go ahead and figure out how to do that. What I want to know are basically what are the over-under odds on winning and losing. Take a few minutes to deal with that, and then we'll go through it together. And then today we'll be doing notes on the next section in the book, which is the last section of content for the year. Today we'll be talking about the meaning of probability. Today we'll be talking about the meaning of probability, which is basically your main primer to AP statistics. Of course, all of this stuff is radically more complicated than what we're going to talk about today, especially once you start talking about probabilities in the real world or experimental probabilities, which have to be bound by error margins. What we're going to be looking at today, if you want to try and draw an analog to what you study in English, right? Like when you learn English starting from elementary school, you learn the alphabet first in kindergarten. Then you start forming words, and then after you're forming words, then you start forming sentences. After you're done forming sentences, you form paragraphs. And if you get good enough at forming paragraphs, you can form paragraphs into even larger structures. If statistics is the writing of a novel using that mathematics, then this section is just the alphabet. This is just that very first puzzle piece that you can then start fitting together with other broader ideas in order to make larger, more valid constructions. I only give this warning because a lot of people, I've had students get excited about this section in the past of like, oh boy, now that I have the language of statistics, there are all these things I can describe. Not exactly. You have a little bit of learning between here and there. Are there any questions on the warm-up? Like any probing questions about how to do it or what this is talking about, in case it's unclear, because it's kind of a soup of numbers. So we have 5 three-sided dice, and these three-sided dice have 2 red sides and 1 blue side. If you roll a set of 5 of these dice and you get 3 blues, you double your money. If you get 4 or 5 blues, you triple your money. Okay, y'all ready to get going on this? Is anybody out there? Have any of y'all ever played a game involving 3-sided dice?
No.
There's a couple different ways that one can design 3-sided dice. I have a big board game collection, and so I have a few games that use them. Here's a really common shape. It's basically a triangular prism, but with this fancy flat side at one end of it, so that it's obvious which number is pointing upwards. Another really common design is like this, just a flat prism with matching characters at the top of each face so that it's clear which side is up. Yeah, they usually come out like a triangular prism with one rounded end so that it can't land on the rounded end itself. Nonetheless, let's go ahead and get into this. So how is it that we can use the binomial expansion in order to analyze this game? How many events are we having? How many times are we allowing this event to occur before we analyze the outcome?
5.
Yeah, there are 5 events here. And so when it comes to our coefficients, right, we're going to be choosing out of 5 for those coefficients. And so we could go across and we could write 5C0, 5C1, 5C2, 5C3, 5C4, 5C5, right? What's the other way that we can generate the constants there? Where else can we get the constants from for the binomial theorem? We could either use the choosing equation, the combination equation, or we could use Pascal's triangle. So let's go ahead and pull the constants for the binomial expansion off of Pascal's triangle instead. So which row do we want here?
1, 5, 10, 10, 5, 1.
Correct, we want the 5th row, right? And so right here, we know that the constants in our expansion are going to be 1, 5, 10, 10, 5, 1. Okay, and in our binomial probability, what are our 2 possible events? We're interested in cases where this dice will either be red or blue. And what's the chance that it comes up red?
Two-thirds.
The chance that it comes up red and we lose is 2/3, but the chance that it comes up blue and we win for any given dice is
1/3.
1/3. And so now that we have the constants in our binomial expansion, here's what we are actually doing to analyze the potential outcomes for this game and what their chances are. This is to say that we're actually doing red plus blue, then raised to the 5th power. And if we do that, we're going to get the expansion down below. And so we'll start off with the losing outcomes on the left and the winning outcomes on the right. So this is to say 1 times red to the 5th, blue to the 0, so I won't write that because that would just give me 1, plus 5 times red to the 4th, blue to the 1, plus 10 times red cubed times blue squared, plus 10 times red squared, blue cubed, plus 5 times red times blue to the 4th, plus 1 times red to the 0, which is just 1, so I won't write it, times blue to the 5th. Are there any questions on my expansion out to this point? No? Okay. So let's go ahead and analyze just the winners. I'm not actually interested in the losers individually for a reason that I'll talk about in a moment. So does this cause us to win money?
No.
No, this is a loss. This is a loss. This is a loss. All 3 of those are losses. And we could process them individually, but I won't do that for a reason that we're about to talk about. And so these over here are our winners, yeah? Actually, I guess this is a poorly designed gambling game, but that's neither here nor there. Let's just process the question. How do we process this? What is that actually asking us to do? So it'll be 10 times, what do I plug in?
2/3 and then 1/3.
10
2/3
times 2/3 squared times 1/3 cubed. And this right here will give us our probability that we can double our money because this is the odds of getting 3 blue faces. And here I get 0.16. Or actually, let's just go with 0.165. So that is to say that you have a 16.5% chance to double your money. And then let's also process both of these over here. This is the chance that we get 4 blue faces or 5 blue faces. Either one of these outcomes would let us triple our money in this particular ancient alley gambling game. So this will be plus 5 times 2/3. Oh, I'm sorry, we're going to process this one separately over here. 5 times 2/3 times 1/3 to the 4th, and then plus 1/3 to just the 5th on its own. So for this first part right here, this will be 5 times 2/3 times 1/3 to the 4th. So this piece right here is 0.041, which is to say that your chance of rolling 4 blues when you roll these dice is only about 4%. And then this piece right here, 1/3 to the 5th, this is 0.004, which is to say that you have a 0.4% chance of getting all 5 blues and tripling your money. So all in all, you have a 4.5% chance at this game to triple up your money. So how come I didn't calculate the chance of losing? What's another way that I could get this value here? If you were to do, we could subtract what?
0.045 from 1.
Both of these, we'd have to add them up and subtract it. The deal is that red plus blue is going to be 2/3 plus 1/3 raised to the 5th. 1 raised to any power will give us back 1. So we know that all of the probabilities here in our binomial expansion, these all need to add up to 1. So if I have these 3, and I know that in total all of them add up to 1, if I want the chance of losing, this is just going to be equal to 1 minus the chance of winning, 0.165 plus 0.045. And so this is going to be equal to about 1 minus 20-ish%. Yeah, so you have a 0.79% chance of losing. You have a 79% chance of losing in this game. So, hey, if you ever accidentally fall through a time machine and end up in ancient Greece and somebody hands you 3 stick-shaped red and blue, I'm sorry, 5 stick-shaped red and blue dice in an alley, maybe don't play that game. You're probably going to lose. Are there any questions here on this morning's warm-up question, on this particular do now?
No, I guess not.
It's a fancy one, and I basically guarantee something of this variety on the chapter test. It's easy to do once you know how to do it, but boy, if you don't know how to do the binomial expansion with an actual like probabilistic example, this is a nightmare to have this question posed, huh? Also, before we move along to notes, are there any questions about current news? About what's going on in the world right now?